Okay, I think we're about ready to get started. Welcome, everybody. Welcome. Another instance of doing some Rust programming. Today, I have hopefully a lot of things go right in terms of our little 7-segment display development using Rust. A little bit off stream, I updated my schematic a little bit. Not my schematic, but my breadboard a little bit. So it looks a little bit nicer now. Here it is. I basically cleaned up the wiring a lot. I was getting a little bit annoyed with how disorganized it looked. So I looked up some tips online on how you can organize breadboard wiring a little bit and learned that it's a lot better to use some tools like this to go ahead and make your own wires. You know, clip stuff up, bend it, rip it from the insulation, that kind of stuff. But now it's all clean, which is a huge improvement from last time. I'm not sure if any of y'all remember how it looked last time, but this one is just more visually pleasing. You got all these blue wires representing the segments, you know, each individual segment, and you got the yellow representing each digit position. It's just something that I enjoyed doing, really. It took longer than I thought it was going to, but I think the result's pretty nice. And it also allowed us to extend our project to use the second display, because I didn't actually wire up the second display last time. I was only wiring half of it up. But that's all I did. I just wired it up. There hasn't been any changes in the code since I've done it last time. More just cleaning it up and kind of figuring out what's a good style for me when it comes to wiring up the breadboard circuits, because I imagine I want to do this a lot. But yeah, just a little bit of an update about that. The main thing is learning that and then figuring out a even more bare minimum project for Rust was something that I was doing. Still using the Embassy framework, but just something a little bit more simple. And so let me show you what I got for that. Hold on. I also made a bunch of new scenes with new art. If you didn't notice already, the chat looks a little bit different now. We got a little bit of a different overlay going. Above me would be chat. If somebody were saying something, it'd be there. We're going for more of a 4:3 or a square aspect ratio 2, testing that out a little bit, making it a little bit more just organized on the screen, that kind of thing. Just minor updates that I'm trying to do over time on this channel. Excuse me. So if I come into here, we got our VS Code. Now, because it is square, I'm a little bit unsure on how it's going to look on stream over time. Ideally, this matches exactly to 80 width. You know, that's like one of the formatting standards that I've seen Google use and a lot of other people. They have 80 width columns. But this one, because I was zooming it in for the stream, I don't know if it's going to be. And in fact, I'm looking at this bottom here to see if I get like a indicator on which column I'm in, but it's not really showing. Just fine. Okay, well, looks like there's some code that was attached to that. That's kind of funny. Part of my testing was flashing some code onto there, but yeah, in terms of like a bare minimum program, this is kind of it. You know, you got your tags at the top, no standard library, no main. You include some logging crates, Embassy for the package or for the peripheral access crate, panic probe so you don't have to write a panic handler, and then getting this entry keyword from the Cortex MRT crate, so that way you can define your entry point. Like, this is what I am seeing as the bare minimum. You're not really using a whole lot of the embassy HAL stuff. You're more focusing on your own individual board and just what is needed to make it run, and this is that. But I would like to go back and insert this kind of code into what we were doing last time with the 7 segment. Let me get that open, and then we can start debugging, because oh, I just remembered we need a circuit cam. One thing I noticed is I wired this up, I turned it on. By the way, another reason why I organized this is because these wires were kind of getting in the visual way, I was thinking. So this makes it a little bit easier to point to very distinct portions of the board, make it cleaner. But yeah, I gave power to this board. None of these are turning on. So I'm a little bit unsure if the wiring is fully accurate. My game plan probably is going to be this. And speaking of which, this just made me realize I can do something else. What would be the best way to draw? We have one note. Is one note the best way? It could be. It could be. Kind of shows up neat on the screen too. What if I do this? New section. We'll call this Rust STM32. Okay. Then we'll go and we'll call this game plan. What are we doing this? This is 7 segment agenda. Okay. Let me hook up my little bit of a drawing pad here. Don't know if it has charge. I should have prepared this a little bit. Okay. Looks like it has charge. Oh, it is upside down. Mirrored. Okay, is this a test? This is a test. Okay. So I think my plan is to basically validate the SPI outputs with new like bare minimum, what we call boilerplate, I guess, boilerplate Rust. So that way we can make sure that we're at the same starting point as we were last week. Then we're going to well, first, how we validate that? We're going to validate that using the, what was that, waveforms. We're going to hook up the wires. Thoughts on hex 0001? That's probably better. That's a good idea, Gary. That's a great idea. Waveform, signal or logic analyzer. If you can change the title from the mod point of view, feel free to do it. I wonder if you can. If you can, go for it. Okay, logic analyzer. Also, so the chat's here. If I inverted it, that'd probably be better, but that's okay. You don't know to on phone. Okay, yeah, that's fine. No worries. Future improvement. Okay, so if this passes, maybe we should make these checkboxes actually. That would be good. And then let's erase this then. Let's make these checkboxes. Let's make that checkbox a little bit closer. So we got a checkbox here. We got a checkbox here. Then our next thing is going to be, so we validated that the code is at the same spot as last week. We validate that it's actually going out on the waveform logic analyzer. Then we want to write hex FF on 7 segment. seg. Hold on. Where's the undo? There we go. 7 segment. Okay. If we can do that, then we know that we basically have all the logic we need, and we can just start running, really. We validate that with our eyes. With eyes. Validate. With eyes. Draw a little picture there. Sweet. Because then we can just write application level code. Application level code meaning like set up a countdown, right? Countdown on 7 seg. I got a little messy there. 7 seg. And then pretty much the list goes on and on and on. We just keep running. These are just features, nice to have. But basically, I expect to get this done today. And if we're lucky, this. Everything else is kind of a nice to have. So we'll draw a little line. This is going to be our stretch goal. Stretch goal. Oops. Stretch goal. So we got work to do. So we're going to try that out. This pad, working out pretty nice. I like it. Smooth writing. Wacom, some good tabs. All right. One of the things that I was debating on doing is dragging out the example we did. Not the example, but the folder that we did into its own new separate repo that can be accessed by the public, because currently I've just been developing in their examples folder just for ease of comparison. You can see there's a bunch of STM based stuff in here, but I kind of want to make just a brand new thing that I can actually push to GitHub. So we're gonna go ahead and create that, I'm thinking. So what we need is just a quick little command line. And we're just gonna call cargo new, and then this will be the name of our project. So this would be, what would be a good name? Is it gonna be eventually a chess timer? That's what I'm thinking. So time, I don't want to do timer.rs. I want to have it end with rs. I've seen that nomenclature around. So I'm gonna do cargo new chess timer -rs. We'll do that. Okay. Then we're gonna open up code in our chess timer -rs. We can close out of these windows. Make this be the full screen. Cool. If you haven't seen the process for creating a new Rust project, that was it right there. You just call cargo. It's pretty simple. It's pretty nice. And we just got to populate a few files. So based off that example I was showing just a little bit ago, we're going to populate those exact commands back into here where we have this deny. In fact, I might get rid of the deny safe code. I'm not too sure what it does just quite yet, and I know it can work without it, so I'll get rid of that for now just so we know we're in a same state as last time. Okay, so we did that. We're going to need to update our toml to have more dependencies, which we can do with this. I can paste that into here almost. Just need to rename this to be the name of our project, which was chess timer -rs. Okay. Make sure that it didn't convert something. Okay, we're good. How do I undo? Control-Shift-C? Not quite, but this is fine. Rust. No. Chess timer -rs. Okay. Cool. Is there any other dependencies? We can double check that in a second. But first I want to create our cargo our cargo folder, or .cargo folder rather, and our cargo, or no, config.toml. This is our script. Okay. And then, oh shoot, now I can see columns at the bottom. Just a little side tangent there. Let's see, I can go up to 80 here. And then if I fill this with X's, I can get to almost 80. I'm gonna say 60, not 80, but yeah. Okay. What else? We want our build.rs, so that way we can get these command line arguments when we run the linker, so we don't have to worry about memory. Getting the memory.x file in there. It just pulls off of the embassy repo. And I think in terms of boilerplate, that's all that's needed. So if I do a cargo build, it should just compile. Let's see. If not, then I'm just missing something minor, I bet. But I think that's all. Okay, yeah, see, it created unoptimized and debug info. Sick. So now what we need, oh, hold on, what's going on here? Oh, I remember now. So there's this thing with this extension I'm using called Rust Analyzer, where it's looking for particular files, particular configuration, like the compiler we're using and some other settings that I'll pull up in a second. We just need to make a .vs code configuration for that real quick, and then it'll be ready. Just timer rs. Wait, no, we need STM blink. Yeah, so this is what I needed. Let me copy this folder. Sure. Yeah, here we go. So just this toml editor format on save. I'm not actually sure what this is. These might not even be necessary. In fact, I'm gonna get rid of them. I'm pretty sure they're not necessary. Is there anything else needed? I don't think so. So we go into here, but we restart our Rust Analyzer, restart server. That squiggle should go away, hopefully, because I'll read that settings.json and know to use this compiler target and to look for cargo.toml to know where the dependencies are. And there you go. It's not there anymore. Have you ever had that problem? Just have this settings.json in your project. In fact, I'll probably put this, when I compile this, I'll put it in there because it is necessary. So normally you would put a ignore on the VS Code, at least that's the common thing I see on projects, but it's necessary on this. Also with the lock, should you include that? I feel like I feel like this could probably get ignored as well. Cargo.lock. But yeah. Okay. So we got a project. Let us add the embassy code for SPI, which we will get from our repo, not repo, our past project. Let's see. Samples. STMU5. Wherever that's at. Here we go. We want to have this open on this. Actually, we'll just open it from this folder. Encode. Okay. We've probably toggling back and forth between these two projects for a little bit here. So you can see in this other one, I was using the embassy executor. That is the more proper way to do it because now you're linking it into the embassy executor. And if you're going to add more stuff later, it's based off of this library already. So you just be uniformly doing it and you don't have the Cortex MRT. I suspect that this executor is based off of this Cortex MRT, but I could be wrong. That's just my guess. Let's see. So we want to get this peripherals into our project. So this is where we're going to start importing stuff. I'm going to I'm going to insert something new, let P, or we're going to do pack. I like using pack more for peripherals. Pack, it's not defined. We'll let the compiler define the type for us, but we want embassy, we want GPIO. Oh wait, no, we want init. You run this always when you're creating an embassy project. You always kind of need that. Default. Okay. So you got the pack, which stands for peripheral access crate. It's just a terminology that I've been seeing in a lot of the documentation. Try and get rid of these extra stuff so you can just focus on the code. Since we're going to be using embassy's crate with other stuff besides the main call, like we're going to call some more nested stuff, I'm going to split this onto its own line and say use this for GPIO. We're going to go over here and then use. So that way we're calling everything inside of GPIO. Oh wait, we need to do this. There we go. Now we're calling everything. Oh, I got rid of GPIO. Whoops. GPIO. And then I think it's this again. There we go. So now if we call something like pack dot. Well, actually, I don't even remember how it goes. All right, here we got an LED. Let's just start there. So LED, this is going to use the pack. We call it P here, but I'm going to call it pack. We're going to do let mute LED. We'll do my LED. Well, let me do that. Forget how the built-in linter works again. Create an output. New. The pin will be pack dot. I think it's PC7. Okay. Initial output. This is going to be low. Right. We want. It's just low. How do they define it? Yeah, level. That's what it is. Level. Low. And then speed. We're going to do medium speed. Speed. Medium. Thank goodness for that autocorrect or that autocomplete. It's very nice. All right, what we got here? We got some warnings. Remove this mute. That's right. They don't like this. You have to do camel case, I believe. So my LED, does that get complained about? This does get complained about. Non-snake case. Convert the identifier to snake case. So snake, this is camel case. Snake case is this, no? Where you just have the same. Oh, that's not snake case. Snake case is like this. So we want this, but it complained about us having that name. Did it not? My LED? Oh no, it didn't. Okay, we're good. They're saying if it's intentional that you're not using it, they want you to preface it with a underscore. Must be a convention to like get it to compile without that squiggle. If you know you want that variable, but you're just not going to use it right away. Okay. Next thing we're going to do, well, actually it's should already be turned on, thinking about it. This is creating a new instance of an LED. This is defaulting it to low. We want to default it to high though, so that way we can see instantly what's going on. I should be able to just compile this. Do cargo build. They don't like that we made it mute. That makes sense. We're not actually doing anything else in code to mutate it. If it's intentional, okay, it's unused. Also makes sense. So let's try this naming convention. They're saying that should make that warning go away. And it does. Okay. Just a convention. Good to know. So you probably search for all your underscores variables, you know? If you did a search and you just did underscore and you did it like this, you could instantly find those underscores. Although, of course, I'm searching all files, but like for this, you'd find those underscore variables so you could instantly see, hey, which ones did I not use again? That's cool. Okay. We already built it, so we're gonna go ahead and do a cargo run. All right. Not sure if you guys caught that, but this LED turned on because we just programmed it to, and it's spamming. And I mean spamming. It really wants to tell us that it's inside the loop, because it is. So, cool. And if we go to the top of this, it should say hello world, but I think I let it run for too long. Yeah, we ran out of buffer in our command line, our command prompt, but that's okay. All right, that is set up. Now, let's get into not blank ERS. We want this example. So this one configured an SPI. Welcome, Johnny. Welcome, welcome. This one did an SPI. So we're going to create an SPI instance. I recall this library having an example that didn't use from SPI, but we just want to make sure we can still do SPI with this bare minimum. We'll start with that. So we're going to do let mute my SPI. Okay. And at least according to this, that's going to come later. We need to set a configuration first. I only knew all this because I did this before, and this is how the example was. But if you're starting from scratch, you want to make sure you're going to be looking in the MSC underscore STM32 document page. That's the key here. All right, we'll do SPI config first, just like it said. Okay. This is going to be equal to, is it output? No. It is just a config. It's looking for a config, default, and that should have automatically included it here, which you can see right there. Okay. We're then going to declare a Hertz value. So SPI underscore config. This is going to be frequency. Interesting. It has a member name frequency. You're just supposed to know that. Dot frequency. It's not actually linking to the proper thing. That's something I wouldn't have expected. What's this one linking to? This one's saying it's coming from MSC. Okay, yeah. Maybe it's because I'm missing the SPI. We need to... Maybe that was thinking of a different config. I could see that. We want to make sure we're defining the SPI library. And this config is now pulling from the SPI. Okay, perfect. So if I do SPI config dot frequency, there we go. We can set that equal to... Are we going to get the Hertz conversion macro? Or are they calling it a macro? They're calling it a struct. Just a struct. It automatically will take that value and put it in there. Okay. Hertz. And we're going to do 10,000. So this is how fast our SPI is going to be running. We chose that number because these displays, they have a maximum rate of 100, or not 100, 10 kilohertz. All right. Now we are going to configure our SPI. So this is where we say let mute perhaps my SPI. We'll just do my SPI first. My SPI is going to be equal to this instance we're going to create. So SPI new. And this is where we get to start writing the exact pins. Luckily, I already did this from last stream, so we can kind of speed it up again. First, we need to figure out which SPI module we're using. So we're using 1. Then we need to assign a clock, which we saw on the data sheet that is wired to PA5. Then we can do our MISO pin. So master in slave out pin, data coming in pin. Pack dot, we put it on PA7. Same thing for MISO, master in slave out. Data going out. This is more relevant for us since we're writing to the screen. PA6. There's a setting for having DMA on transmissions. We are not going to use DMA for this simple example, so we're going to use this tag called no DMA, which should get auto imported here. Same thing here, no DMA. And then the config, we're going to use the config from before, which we called SPI_config. That way it knows what frequency to run at and all the other default settings that associate with initializing SPI. Okay, we created my SPI. It's suggesting we also create a chip select pin, which is just a regular GPIO pin, right? It's just like the my LED up on line 12. This is just another digital output that we're creating. That's what output stands for. But this one we're going to be using for chip select. In fact, we should do like display chip select to be more specific. Display chip select. Because there might be multiple chip selects. In fact, you should probably put chip select and then the words, so that way you're more organized. Chip select display. PD14 is the one we use. PD14. And then our level, we can just default that to low. Actually, we want to do it to high, I think, because it's dependent on how SPI is running. We want to do very high for this. I do know that. Okay, we're getting one error here. Cannot assign to SPI config. That SPI config is not declared as mutable. Oh, we need to make this mutable right here. Cool, easy. Okay. So because we're not using these right away, we're going to go ahead and make those underscores so that way we know that we are creating it once and not actually doing much with it. This should at least create a high line for the chip select. We're going to go ahead and build this just to make sure we're good this far. Okay, that was easy. We're also going to program it with that code. This should start looping forever, but we're going to close that. That's just our indicator that it programmed. Then we're going to come over here to the circuit cam, and we're going to need to add in our SPI sniffers, is what I like to call them. But really what I mean is our lines here. We have these wires that we're eventually going to hook up to look at our IC, but we're not at that step yet. We want to just make sure that the pins coming out of the microcontroller are at the state that we think they should be. So first things first, we need to ground the microcontroller. Every time I pick up this thing, I don't know what it is. But as soon as I pick this thing up, I feel like that's when it gets power. It's really an anomaly. Also, to me, this tells me that this segment is not wired. The wire is not making full connection. So let's quickly figure out what that is. But this is reassuring to me because this tells me that most of the wires are good. Unless this is broken, but I kind of doubt that's the case. We're going to go back really quick to, was it this one? Yeah. This screen here. Also, what happened to the music? That's kind of silly. The music froze. Not sure why. Deep house. Yeah, I was not that far into the set. That's funny. What were we doing? Oh yeah. Data sheet. Here we go. So they're saying F. They're saying F is the key here, which would be the third pin from the top. So we'll go ahead and double check that pin. Cricket cam. Third from the top. It could also be that the cable that it is connecting to at this end, because I had to do like a split, could be the cable up here is not in the right row. So this would be the middle wire. And I'm pretty sure that's the case. I think it's one too many over. Oh no, that looks right, never mind. That looks right. It's not lighting up, huh? Okay, what happens if we remove this wire right here? Okay. And then we remove this wire. Oh yeah, see, that's not doing anything. Picking that up, you see, it's not actually affecting it in any way. So that means the other end might not be connected. Ah, that is right. This side is not in the right spot. I see it. We'll go ahead and put this side back in where it should be. We need to adjust this side. That's the one thing with breadboards is they can get really tight, as you see there. And then boom. Okay. Yeah, that's right. We got A8s. So power is good. Power's good. We go back to our list here. Was that one of our milestones we wanted to get? Is that one of the milestones? Validate SPI outputs. No, not quite, but that should have been one of them. In fact, we could append that to the list. That's definitely something we wanted to do. Let's validate wiring. Is there a way? This is my first time kind of trying out this OneNote thing here. Lasso select, let's do that. Oh, that's not quite right. Let's do that again. Oh, almost there. Okay. Let's move that down. Perfect. Okay. Oh, not lasso select anymore. Shiz is wired right. a big ol' check for that one. That's a great first start. Just have to keep turning this on and off, I guess, while the stream's going. That's not so bad. Okay, sweet. Easy first milestone. Kind of did the work off stream, so that made it easy to achieve, but still needed to be validated. All right. So we wanted to wire, that's right, we wanted to wire this up. So we're gonna need the data sheet for this board again. I know this thing. Because we want to know which of these pins to connect to on the board. Which of these pins. So if I do a search, oh my goodness, I did too many buttons at once. Okay, if I do a search for CS, perhaps? How about do CLK, clock? There's only so many clock signals that this thing's gonna have outgoing, and it looks like that first finding would have been the one. Even though it's not here. Maybe it's under SCK, that's possible. It is, not SAI. We want SPI. Okay, here we go. So these are the pins we want. We have a SCK, a MISO, MOSI, CS pin, and then is that it? That might be it. 1, 2, 3, 4. That seems right. All right, let's wire that up. The PA5. I'm just gonna leave it on this screen for the stream. I think it's a little bit easier. I still don't know the answer as to why when I pick up this board, everything turns on magically. In fact, I'm gonna turn that off just in case I'm like shorting something every single time this thing's floating. Not really intended, but it is happening. Okay. So we got a ground pin here. We're going to take orange here and make that our SCK, because we're just going to go down the line. Actually, let's start from the bottom and work our way up. So D10, right? D10's there. And I'm going to find D10 on this thing. Seems to be right about here. Also notice the music stops, so I'm going to have to figure out why it's doing that. 9, 10. There we go. Right? Yeah, D10. There we go. D11, D12, D13, just up the line. Really simple stuff. Okay. Is that all right? Yeah. So that's wired just like so. Look how neat that is. Look at that. That's like a perfect rainbow, a perfect arch. Just following this bus, essentially, all together. I like that a lot. Okay, we can minimize that. Then we're going to go over to waveforms. This is where we're going to validate. So if I give power to this thing, look, I gave power, green light on, no power on this. But watch the magic as I lift this thing up. Okay, nothing happened. Oh, I've had this before, actually, I feel like. I think there might be a floating ground. What happens if I disconnect this ground? So as soon as I feel like it has to do with these wires, these supply between the two. It has to be something grounding. differently. I just put that in a random pin. What am I doing? That's not ground. That's ground. Whatever, we'll continue. Our goal wasn't really to validate that this turns on yet. Just validating that we are outputting on our function or our logic analyzer. So if I do SPI, actually no, we want like the raw signals first. So signal 0, add signal 1, add signal 2, add signal 2, add signal 3, add. Some of these we shouldn't be seeing anything on. Some of them we should be seeing some stuff on. Does it make sense that we only see a pulled high on 0? Well, let's look at our code. I would say yeah, probably. PD14 should be high. Everything else should be defaulted to low. That would make sense to me. Let's check if this PD14 R0. It is. Okay, so this is set up, at least initialized correctly. Let's try and write. Let's just try and write some data. I've never actually used the SPI module, so let's see. SPI. Oh wait, we want my SPI, and in fact, we can do this now. My underscore SPI. Is there a write? There is a write. We're going to write, not using DMA. We don't want to use DMA. Blocking write. That's probably fine. I'm usually when I see blocking write, that means that there is a busy while loop in it. But we can just try and write words. Okay, words. It's of data type an array, a buffer array, or a what do they call it? A borrowed array. So if I were to do this up here, let's data test data equal to, how do I do arrays in Rust? I actually forgot. And it looks like I can do maybe this. Is that gonna work? 1? I don't know if that's how you initialize it just quite. What happens if I do that? We'll know what to do off of that. Syntax error, expected semicolon. Okay, what if I do it without setting the size? Instead, put this. It's not like that. Did not like that one bit, in fact. 10% of test data. Isn't that how you do that? It's looking for this. W is a template or generic. I believe that's how they call it in Rust. And that generic is used. Oh, that's a trait. Word is a very specific thing. Okay. You can see now that I need to slow down a little bit because I don't actually know how this works just quite. I'll have to figure that out. Let's read this. So word is a trait that they defined, which is part of the DMA module, really. Huh. I see a public trait word up here, which is a config. Word implementation. Config. So where's word implementation? If I search for word imp, there it is. Word imply. What's up, Sean? Howdy. Howdy, howdy. How you doing? You enjoying the YouTube Rust stream? In that 1080p? At least I hope it is. Okay. Maybe that's not where I need to go. Unknown. Yeah, it doesn't know what to call it. Maybe I need to define it as a Rust. But what we can do, maybe to speed this up, is if we look up in the embassy library, they manually did a... Okay, at buff, it's 10 AP. Okay, sick. Love to see it. Here's the key. They made this. They didn't even need to define this. This is not how you do it in Rust. You say let test data, and you put it around. You put the brackets around the variable you want to put into it. But now it's an array that, I guess, well, hold on. If I put a comma here and put a different value, what would happen? 2. Okay, so this is how you do it in Rust. You define your data type as an integer 32 in this case, and then you define how large that array is going to be. In this case is 2. We're going to do A5, 5A. Okay. A5, 5A. Which gives us 1010, 1010. So nice and easy. We probably need to make this mutable to be referenced, is my guess, based off that example. And they just, oh, okay, you have to define it as mutable here. Interesting. What happens if I instead put this in the context of the loop? Will that squiggle go away? It doesn't go away. What do we got here? Word is not satisfied by the other types. It actually needs to be word, I think. Okay. Oh, interesting. You have a description of what mutable mutes are. How about this? We need, it looks like we're gonna need words. So what would be the best way to do this? I think if I, W's word, hold on. Blocking right. This we know is an array with a word in it. We need to figure out how to make this word. I think that's just the only missing element. So how about I go SPI here, and then we search up word. This works. Word. This is a whole file. Word size. Public trait word. Public trait word. This is, okay, hold on. This is a macro. Implement word. Implement word 1 byte. So apparently I can call implement word. Maybe you have just this type, and this will be a word. What happens if I do that? U1, U2, U3, U4, how will implement word? It takes 4 arguments, right? It takes 1 argument here, 1 argument here, here, and here. So the size, 1 byte. The literal, 1. The indent, I'm not really sure what that's about. Something about Rust is you can make your own macros. That's how you define. You use this macro rules. This is how you make macros in Rust. And I know you have to put these $signs around particular things. I haven't looked into it too deeply. So I think we can kind of ignore the $sign and treat this more like you have this data type and it's this name, indent. Data type and then this name. Data, oh, the other way around, sorry. Data, no, name is T. This is the data type, indent. Name is bits, the data type is literal. Name is size, data type's indent. Not sure what an indent means. But since they're just calling this a bunch of times, Is this macro public? Let's see. If I try to call that, what would happen? Exclamation point. Crap, what the heck was it called again? It was implement word. Can't remember. Do you need to put the exclamation after? Guess so, because that's what they did down here. So if I do this, does it know what to do? It doesn't look like it. Has no idea what the heck that is. Cannot find macro in the scope. Well, it doesn't say public, so I could see how this is not accessible external. Could be a more like a static function. Okay. Word size. What's this? So could be something we can access. We're in the SPI crate, I think, right now. Maybe not. There's SPI here. I don't think we are. Let's go to SPI. Okay, I guess that was. And then let's look at the outline of this. These are all of our different tree hierarchies in the Rust file. I think what we want... Well, okay. We could start from that function that we're trying to make, which was something about writing, right? Blocking write, which we may not see in any of these because it might be attached to one of these higher functions, or not functions, structs. Okay, well, this is just a struct. It's not that. I'm gonna drop compute baud rate, compute frequency, external registers. I'm guessing is what that is. I'm not seeing that exact function. How happens if I click on this blocking right? So it's inside of another context. It's inside of whatever this is. This is SPI, implement SPI instead of implement SPI. It's like a constructor. It's what I believe. Yeah, okay, you can see here. New, RX only, TX only, TX. Sub gigahertz? Holy crap. That's crazy. Inner, set config, current config, set word size. Do we need to configure that? I like to think we don't. This is a read. Blocking right. We're back to here. Really comes down to this. It's words. Or word and words. Transfer the word. Makes sense to me. We just gotta figure out how this word works. And I think this is just one of the real learning curves of Rust. Figuring out where stuff is, what stuff means what. So we don't need to call self. That's already doing it just by calling the function. This is for the constructor only. Do we need to do something like this? Oh, that's not our code. Let's get rid of imply word. Any ideas? Any Rust pros in the chat? SPI word is not satisfied. Word. Word. Public trait. Word. Where this word plus sealed word, like I'm not too sure what that means. Word sizes usable for SPI. Is that what this is? This is word implement. What file? Is this the same file? Must be. Bin trait, DMN trait. What happens if I look things up here? SPI and embassy. Does it have any extra information? I feel like it's not gonna. Blocking right. Blocking right. Nothing particular. Limitations on foreign type. Implementers. U4. What is U4? Where are we? DMA word U4. Oh, that's right. These are all referencing parts of the DMA. So is the blocking right only useful if you are using DMA? That's always possible. Is there any other option to write? This writes the contents of data on MOSI and puts the received data on MISO in data at the same time. Okay, that's not quite what we want. Blocking bidirectional transfer. You read and write. Nah, not quite. Transfer, you're transferring data from here to here. What if I just did write? This write uses a straight up a TMA reference. Where TX, is there TX in here? There isn't, but it is still using a word generic. How about this? We open up the Rust book and stop guessing. Rust book, generics. So, yeah, let's start with this. Been using generics. Yep, that's right. Show us an example with the generic. That'd be great. Or I'm not seeing said generic. Maybe it's on the next page. Generic data types. So, place generics in the signature of the function where I usually specify the data types and return value. Do you see a generic in here? I see a name of variable and then the variable itself, or the data type of the variable. And these have it. Two functions that differ only in their names and their types of signature. Oh, this can be an example. Here we go. Here we go. All right. When we use a parameter in the body of the function, we have to declare the parameter name in the signature so the compiler knows what that name means. Similarly, when we use a type parameter name in the function signature, we have to declare a type parameter name before we use it. To define the generic largest function here, place type name declarations inside of angle brackets. So the name is T. We now have T and it has T, and it also returns T, but it's all the same type for T or template. So this is what our function looked like, right? W, W, W. But they defined, instead of it being a generic that just takes everything, I just realized it's probably too small to even read well. Instead of being a generic that just takes everything, it only takes a word data type. If I remember correctly, that is what's going on. Let's find an example where they define an exact data type for that template or that generic. Defining a trait. This is just traits. The trait is word in our case. I think that's how it goes. Not quite. Here we go. Trait bound syntax. The implement trait syntax works for straightforward cases, but is actually a syntax sugar for a longer form known as trait bound, and it looks like this. The longer form is equivalent to the example in the previous section, but is more verbose. We place trait bounds with the declaration of the generic type parameter after the colon, which is here. We got this trait, got generic type. You can use this, but I guess we're looking at legacy code. What's the difference here? The difference is, what's this question? Do I do door camp? Oh, do I door camp? I'm looking for some Rust Zerg. I'm looking for some people to be part of my Zerg so we can door camp together. You know, I'm mostly, carrying the Rustation army right now. So I'm looking for some more door campers. We got summary. Item 1, item 2. Well, unfortunately I didn't write this library. Oh, hold on. Clear trait bounds with where clauses. Using too many trait bounds has its downside. Each generic has its own trait bounds, so functions with multiple generic type parameters can contain lots of trait bound information between the function's name and its parameter list, making the function signature hard to read. Yeah, it's already hard to read, so yes. For this reason, Rust has alternative syntax for specifying trait bounds inside of a where clause after the function's signature. So instead of writing this, let's see, can I even parse this? Some function, okay, a generic T that can be a display or a clone. This plus means one or the other, okay. It also has a generic for U that can be clone or a trait of debug. Okay, those get passed in. This is the generic. It's going to be named lowercase t. This is generic lowercase u. This is the where clause. You just put the two generics. All right, that's fine. You then have that same argument parameter section, but now you have where. Where t can be display or clone. U can be clone or debug. I am glad I read this because that clears this up majorly. Generic W has to be type word. But that's the thing, we are seeing where clauses. We are seeing where clauses in our code. So let's try to go back to that. We can also look at this implement word macro too. Let's start from the top. We want to write this. We don't have type word. We got to figure out how to implement type word. DMA has something called type word. So what if we do this word? But from DMA, this is SAI. What is what? Word. Word. What? Is this a thing? Can I do... Shit, I don't know. We'll do this. Word. Just keeps going to SIE. I don't quite understand that. Yeah, I don't really want that. It's importing it too. Let's just comment that part out. We go to SPI. See, words right here. That's part of DMA. And word size is public. Module sealed. The trait word exists, which it's getting from sealed, or it can be default, or it can be copy, or it can be static. Interesting. Sealed word. What is this sealed word? Well, here's sealed, but sealed is not public, which means it's only in the scope of this file. So if we import words, it's not going to incorporate this. There's got to be another way to access this. Surely it's not closed off. Do I need DMA to do it? We have an example here. Does he do it anywhere in this function? Or in this library? If we search SPI, do we find anything? Ooh. No hits. No hits. SPI was not used in the creation of Quad. Bummer. Really hoping they used I2C. That makes a lot of sense. That's just our example. We're going to go back here. What about new? Do we need to implement our DMA? Let's look at DMA a little bit. So we created something called MySPI. It has no DMA. No DMA exists in the DMA file. No DMA placeholder. You may pass this in place of a real DMA channel when creating a driver to indicate it should not use DMA. This often causes async functionality to not be available on the instance, leaving only blocking functionality. Okay, so based on that sentence right there, I'm thinking block and write should work. Issue is I don't know how to use it. Word. 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 Public trait. Word. But implement word's not. It needs sealed. Sealed's not. Oh wait, but word can be word. Oh my gosh. Word. Okay, but is word this is your are you public? Are you public word? Tell me, are you public? Word. DMA word sealed. These are all implementations. Do I do U1? Is that how I'm supposed to do? U1? What happens if I do U1? U1. SAI. It keeps picking up SAI. Why does it think SAI? Shouldn't it be DMA? I'm so confused. Why? Okay, I mean, if the word in this is the same as the word in DMA. Oh, what's this? Use create public. Word. Got it. Well, Okay. We'll just do this then. That's just fine. No biggie. We do test. Oh, sorry. Let mute test word. DMA word trait equal to this. Is that a thing? And then I come over here and do test. Missing reference, expected reference. So what if I do this? Mismatch type, expected reference found. Bruv. Word plus static. So it sees that I passed in this word type. Okay. Does this need to be something? Okay, hold on. Cannot be made into an object. The trait cannot be made an object because it requires self-size. For a trait to be object safe, it needs to allow building a vtable to, oh my gosh. Okay, so the sum of it is I can't do it that way, but the trait bound is not satisfied. The following other type implement trait. So we need to legit use one of these. Oh, U8. Hold on. U8? You're telling me that works? So if I go U8, U8, that's a thing? Oh, I don't see anything. I don't know where it's getting that from. U8. Hold on. Not quite. U8. Does that work? Need test. Variable does not need to be mutable. Okay, sure. Oh, alright. Cannot borrow my SPI as mutable, as it is not declared as mutable. Make this mutable. Okay. Unused results. So then we do unwrap. Shoot. Okay. Okay, huh. Can we make sense of that? What did we just learn? So this function is looking for some generic type. They're calling it word, where we needed to go and see all the implementations of words so we could see these different types. So it's kind of like a type def. If it's C, seems like generic's a type def a little bit. So if we do a type def, it's saying that we could go into, where was it? We could go here, and then go here, and then go here, and see that it was implemented here as U8. Okay. Alright. That is interesting. Huh. A little bit of a crazy tangent, but okay. I think we get it. But theoretically, A5 should be being written a bunch of times. If I do this right. Let's try and compile. Okay. Compiled pretty nicely. We hit run. Okay. A little bit of a spoiler. Okay. A little bit of a spoiler. But I am seeing action over here. I am seeing action. That is some Rust SPI. Ladies and gentlemen. Rust SPI. let's check this data too. So you can see chip select is just being held high all the time. Normally you need to be toggling that chip select, I believe. Okay, but we're writing so often that it's just gonna stay high. DIO2 is low because we're not actually writing anything out of that. This is our input data to the chip, to our microcontroller. This is our output data. We write whenever we turn on the clock. And then what we need to do probably now is I'm gonna make a actual SPI signal. So our chip select 0, yep, active high. We're going to say our clock is D3. Okay. And then our data is D1. 8 bits. Yep, this looks right to me. So now if I run this, they're getting some signal called 2D. 2D, does that make sense? We wanted A5, but we're getting 2D. Let's pull up a calculator. Maybe it's inverse. Calculator. Go to programmer. Oh, sorry, wrong thing. Programmer, here we go. Now we're gonna pause this because that's just going forever. All right, programmer. We got the bits out. Hex 2D is what we're seeing. Okay. 2D. That is not quite what I was expecting. A5. A5. This is 4 if you're starting from this side. This would be 4 if this was your lowest bit position. And this would be D. Sorry. Yes. No, wait, hold on. We gotta invert it. This would be something. It's okay though. Either way, that's not the data I was expecting. A little bit of a shocker there. What's something we could do? What happens if we do FF? Let's try that. FF. So same thing. We're gonna hit run, which would build and then run. And we're gonna go over to the waveform. Pause it. Okay, this one's showing FF. Interesting. So FF is working there, but perhaps not for A5. What's about 0.1? Let's do 0.1. I'm gonna reprogram it off stream. Not off stream, but off screen. Okay. I'm gonna run it. Okay, this is showing fine. 1. Yeah. Did it not like A5? I'm gonna try A5 again. A5. I wonder if there's a glitch. Okay, I just programmed with A5. Oh. What? Are you kidding me? Oh, wait, hold on. Oh, here we go. I think this is the source of the problem. It's not. It wasn't sampling correctly, I think. Did I see A5 just fine right there? But now I'm seeing 2D because it's off. It's off. I think I need to configure more settings. I also think it's having an issue because I'm just keeping chip select high all the time. So it's just reading everything. I think it has to do with that. So what if I do instead in the code in the code, I make sure that I'm writing the chip select high when I need to. So what do we got here? CS display set high there. In fact, we're going to set it low immediately after. Set low. I think that will give us the intended results, the like peak results we're looking for. Oh, this needs to be mutable. Thank you, Rust compiler. Okay, that's sleeping. Switch over to waveform. There we go. That's much better. So while it's live, it's seeing that. What happens if I want to write 2 messages? I wonder. How can Word handle this? I think I'm seeing how this framework works. And it's feeling pretty awesome. U16, A5, 5A. Or better yet, can I do this? Can I do U8? Can I do 2 separate ones? Like this? And then we do, what is it? 2? Wasn't it something like this? Ah, it doesn't like that. Word is not satisfied. Okay. If I did U16 when it's like that. Yeah, it doesn't like that. I guess it's just because I'm writing one word. This function allows you to write one word. Okay, no worries. Okay, 55A. So theoretically, cargo run's just gonna work. No problem. Oh. Oh. Okay. It did not work. It did not work. That's interesting. Huh. So this needs to be something else. It's hitting on hello world and it's just stopping, and it's also getting stuck in the, in fact, let's get rid of some of these other ones. Now that we have an SPI line that we can trust, let's get rid of some of those other ones. It's stuck in the chip select is high, which means it's getting stuck. It's getting stuck right here. And I'm trying to see if any of this shows that. If you had a actual handler based off of the result rather than using unwrap, this would be what would happen. It's getting stuck here though. While loop, infinite while loop at unwrap, which is right. This is correct behavior, but it's more that we don't understand how blocking right functions. So we had to figure this part out. I think it's because this really does need to be in a bit, and you can even see it here, size 8. So to me, that sounds like that would be a byte. Although this one says size 4, maybe that's the length. No, that wouldn't make sense. TX word. Transfer one word at a time. I don't think that 8 is correct. Were these implements here? Yeah, it was. Oh, bro. It only says U on 8. It does not say 16. Oh, 16's right here. Never mind. Never mind. I misspell it? No, it's U16, right? U16. If I did U8, what would happen? U8. It doesn't know to attach it to the word thing. Apparently. So if I had a bunch of data that I wanted to send out, how could I cycle through that? What's the key? What is the key? I'm also surprised that you don't need a semicolon there. I feel like you would need it, but when it's not there, it's just saying like you're gonna return this function. So I guess I can see that too. It's not completely out of place. Liking right definitely is intended to support more words. I need to define that this U8 is a word, not just a regular U8 maybe. Big U8. U8. Mod word implement. That's not public. U8 is here. U16 is here. Word implement. These are different versions of word implement. I wonder which one it's using. U8 is this. U16 is this. Huh. Real key is this. Oh, I'm just now realizing this. Am I a student? I'm not a student. I am graduated. I used to be a student, but I'm on the continuous learning. Lag seeing. That's kind of funny because I didn't see that for a while. And if that's your name, that's pretty fitting. Are you student yourself? Unit 8. Unwrap. We just need to figure out how to make this an array. If we're doing, yeah, nice. Are you a student, university, college, high school, kindergarten? Let's see here. And are you learning Rust? That's the next question. Are you two learning Rust? We're gonna do test array. And we're going to call this U8. U8. I used to be a student though, once upon a time. During the COVID year as well. You saw that you used to stream games, so you're wondering, gosh dang, I am going to move this chat box up because I actually don't know why my multi-stream is not showing your chat messages. I'm gonna do something really quick. Do one of these. Oh. One of these. One of these. Okay. I asked because I saw you used to stream games, so I was wondering since when did you learn? Yeah. Without doxing the exact college I went to university. in the US and studied computer engineering, and did that for about 5 years. And when I was streaming games, I was doing that when I was in high school mostly, here and there. Actually, yeah, when I was in high school, I was streaming games, and I was doing that for a number of years. And then when I went to college, I kind of stopped the streaming and decided, you know what, I want to try something new. So I decided to take the passion I had for gaming back then and join some kind of club at my college that was engineering related. And I came from a very competitive esports scene, so I joined a club that had a competition involved. So those hours I used for grinding Counter-Strike, because that was the game I mostly played, I used to grind a skill set for that club instead. The club was robotics, so I was learning how to do these embedded systems for robotics. It started off with Arduino, but I kind of just like redirected that passion, and that kind of motivated me to try and treat life as like a game in a way, you know? When I approached it from a game perspective, it became less of a chore and more like fun. Because then I started to compare, like, okay, all these other top engineers in the world, they dedicated some time to get good at whatever they're doing. So why can't I do that? Why can't I make this the best possible attempt that I can? And so I learned mostly C stuff in college, and C++ and Python. But then I graduated and I got a job, and they also were using C, but I found out that there's some newer stuff in the embedded world that I kind of wanted to experiment and explore. That's where Rust comes in. Rust is that new frontier a little bit in the embedded world. I even put a link to this document that the White House put out about like a month ago, I think, where they just name Rust as a possible safe solution for memory safety when you're developing new applications. And I was thinking, you know what, why not check this out? Why not take a recommendation from the US government and see what they have been studying? Because the security flaws that they mention, there's a ton of content on YouTube and on Twitch, you know, talking about C and different languages having security flaws, and they're able to make a living because they're exploiting these security flaws. But Rust kind of fixes a lot of that, so I can make projects that I maybe don't even need to worry about those security flaws as much, because my ultimate like interest is to see like how shit works. How can I make cool stuff, you know? And if I can make stuff that's just secure, why not? I'm sure there'll be jobs for it in the future. One of the things I was told is you always got to keep learning, even after college, if you want to stay at the top of the top, I guess. So, yeah, you saw I used to stream games. This is where they kind of pivoted away from that. I still play games here and there, but definitely not to the same extent that I was playing back in my prime of Counter-Strike, let's say. It's kind of like you have to have the self-motivation to go do something. In Counter-Strike, I had the motivation to be really good at it. I wanted to be esports pro, you know, do that lifestyle. But it was hard. And eventually, life kept moving, and I was not getting better at Counter-Strike. So, you know, you had to realize, is this going to be the pathway you take, or is there going to be a different way to do it? So I pivoted. And so, yeah, we are now learning Rust because we want to try new stuff and pivot, be malleable, or in Rust's term, mutable. So yeah. What about you though? How far into school are you? If there's anybody else in school, I'd love to hear it. In terms of this, I really would like to figure out how to counter this. I would like to make it so I could send an array into this function. I'm kind of thinking that I just need to do something like this, where I go like word U8. And then 1. And then I do this. It didn't like that. Does this need to be a semicolon? Okay, it didn't like that either. It sees this, but doesn't actually use it. I think we already tested this out. I think it failed. This is where my rookiness with Rust is really showing, because I think this is probably like a trivial, maybe not trivial, but like a common thing you'd probably see no matter the framework you use. You get some kind of trait that's custom made for their library, and now you need to figure out how to manipulate it for your use case. And this is where I'm calling all those SMEs, all those subject matter experts out there. I love some guidance. I think if we all learn this together, we could make Rust be the next big thing. Fortunately, a little bit tough being on this battle alone. At least nobody I know personally is a deep Rustation person. Okay, so what happens if I do this? Because obviously it liked it without it. Good for you. Similar journey. You've been using Rust since a few years, but you made web apps and GUI. It got boring. You decided to go back into uni last year. Dang. I'm sorry to hear that it was a little bit boring over time. I have a friend who mentioned that doing the same kind of web app over and over can be a little bit boring. A GUI app can be a bit boring. Most of them are in C++, but it makes you like Rust even more. Okay, that I can believe. I can totally believe that. In fact, I feel like I was reading stuff on Reddit where they say Rust made them a better programmer. Is there a particular thing that's like you're in C++ that you're writing and you're like, man, if this was in Rust, it'd be so easy? Like, is there a particular concept? I'm like trying to think back. Like day to day, I mostly use C. So like C++, even that's getting more rusty as the days continue for me. What if I do 1? Didn't we try this already? I'm pretty sure we did. This is no different than what I did down here, lol. But maybe I need to... No, that's not right. What if I look up on Google build system? Oh, okay, I can totally imagine that. You don't even need to elaborate that. I mean, even in C, I can get annoyed with a classic make file or a C make. You can use the same tools if you're doing in C++. The cargo seems just so straightforward. Granted, my examples have been pretty small. Okay, I've not been making big projects So cargo may get annoying later. I don't know, in your experience, if you've been using it with web apps or GUIs, maybe it's not as bad. But yeah, build systems, that's a great one. Okay, we want to figure out Rust array of generic structs or vector. Let's see what this shows us. Okay, that's not quite what I'm looking for. We want traits, Rust array generic or of traits, I guess. This is a vector again. I'm not quite looking for vectors. Is this just talking about traits? I think it is. Let's see, where is this in the book? How was the compile time looking like when you were doing Rust projects? If it was a bigger project, I'm curious how long, and if the compiling ever got annoying, or if it was fine because you just compile it once, it gets super big, yeah, whatever, but then you just keep cargo building it. Maybe the benefit's the same in terms of the makefile, you know, you're just compiling the things you need to, minus the actual checking that the cargo method does on Rust. What are we looking at here? Hey, look, it's a GUI example. Okay, but this is the implementation for drawing. Quite what I want. What if I instead... Your own system's pretty good? Okay. I don't even see a downside with Rust then. I hear people complain, oh, the compile time takes too long. Oh, we can't be doing that. A compiler's gonna take forever compared to our giant C project. Really? What's worse, having a long compiler or spending a week because you can't figure out that you were pointing to unaccessible memory? I think Rust is it. Get better at designing. What if you're straight out of college? I feel like if you're starting out of college, it shouldn't be expected that you just know the stuff. Okay, hold on, what we got here? Like if you're getting put on a project and using Rust, you're less likely to make these mistakes. It's long in production. Okay. Thank you for correcting me on that. If it's production code, there you go. But still, you just have to compile it once, and then you push it to production. Also, was this for your own project, or was this for a job, like a company's project? Maybe I just need to mute. I'm just surprised because they, well, maybe I should look up this SPI blocking in place. Oh, excuse me. Oh, maybe because it's not compiling. Let's do this, where we get rid of that. We uncomment this. We put this back to just being a normal, mutable array. Okay, what if I did like something like this? Oh wait, 5A. Right? Oh, interesting. 5A. And then another Rust stream. That's right. That's right. We're looking for some people to be our Zerg. We want to be Zerging people. Maybe this needs to be mutable. And why am I passing A5 to that test array? Yeah, don't like that. Figured. It's just like this. I feel like I would have tried that already. Oh, but they just put it without that. Hold on. Yeah, still didn't like it. Test array, yeah. That was worth a shot. When are you joining us, Philip? I do U8. This is not gonna work. Yeah, damn. Oh wait, this needs to be semicolon. Doesn't like something. Expected semicolon? Python and some JS for work. Okay, I see. Yeah, you're coming from the web dev side of things. Have you ever considered doing embedded stuff? Because that's where I'm coming from. Django apps, yep, that makes sense. So the Python was just your backends for the database. That's pretty common. I think was mine Django? Yeah, I think I used, oh, did I use Django? No, I used MongoDB for my database, and then I used Flask, but that was just a basic class project. Nothing too crazy. If I were to do a web dev project again, I'd probably try Rust with the backend if I'm able to. I was looking at something called Tari. I think that was something that was interesting to me. Using the web frameworks to port it to a native app. If I was like later on in my projects, I kind of want to have a GUI that graphs live data. So if I have like a robot that's got an IMU on it, so accelerometer, gyroscope, those kinds of data, I'd like to like map that out, plot it, you know, make that, have that its own project. Call the serial lines for my PC. Just communicate over USB because that's, I mean, no computers really come with a serial COM port. That's not a thing very much. The USB is fine to learn how to do that, but this framework, Embassy framework, has those drivers kind of already built in, so don't have to spend too much time dangling, hopefully, with the USB. But yeah. Okay, how about this? We look up SP. Oh wow, there's a macro even. Hold on, let's use that macro. I didn't even know that was a thing. Unwrap? Where's this macro coming from? DFMT has it already. Okay, sure, we'll do it that way. Sick. Unwrap. Did it wrong. Unwrap. Yeah, well, let me see this. Our display that we got over here. Okay. Our display. It's going to need some functions. Right? There's no way around that. But rather, we're going to need to call some functions. And it's going to need some data. I need to see how much, what's the size of this data? Because if the size of the data needs to be smaller, or sorry, bigger than a byte, I really do need to figure out this issue now. What's the main page for this? Okay, this doesn't quite help me. If I were to do like write hex, it takes an address 0 to 1 and then a 32-bit value. That makes sense to me because it's going to be this 4 positions. Actually, you know what? I feel like that would have been a 16-bit value. Interesting that they made it 32. Maybe if you were to... Oh, okay. Actually, I'm guessing this is what happened. This is what they're meaning. So this library, it can write to this chip, which this chip has 8 channels. I don't have 8 fingers, so I can't do 8. This chip has 8 channels. We have 1 channel for each digit, right? So there we go. 4, 4. 8 in total. That's 32. Bada bing, bada boom. That would be this function. So we do need to write more than 8. That's a little bit of a bummer. Unless the implementation of this write hex function does that for us. But let's see. Value U32. It takes a buffer that it creates. 8 values in this buffer. No, wait, no, it just has to wait. Okay, look, this nomenclature, this is new to me. Is this a 0 with 8 zeros? Like saying you say yes. You're liking your embedded sys class. That's great. You're looking to apply what you're learning in Rust. Okay, so if it's like a entry embedded systems class, I could see you you're probably given a board of some sort, maybe a AVR, Arduino Uno, and Atmega 3028P. 8 zeros. Okay, thank you. This is 8 zeros. 8 zeros and 8. Probably because you're gonna populate this buffer. That's great. I loved my embedded systems class. That was by far my favorite class. Second favorite would have been the FPGA class, but that definitely sparked my enjoyment for this kind of stuff. Okay, base 10 bytes, value. So you pass in the value to this buffer that's mutable. That's also a reference or borrowed buffer. And it returns J. You're going to take J and you're going to pad all the left bytes that aren't being used with 0, I'm assuming. And then you're going to call this function write string, where you pass some stuff and it checks if it's conditional, if it passes or not. Interesting. Writes a write justified integer with sign. Makes sense. We weren't even looking at the right function. Isn't that funny? We needed write hex. Write hex is this one. Same thing. Hex bytes is essentially the same exact thing. Hex formatted integer with sign. So this doesn't use any SPI. Well, we should probably see what this write string is. That's the core of all these. So write string is taking an address, treating this as a char array, calling it string. Max digits, probably 7. I guess defined somewhere. Dots. There are dots you can enable. The result, it can return itself, I think is how it works, or a data error. So, decode mode, which is defined somewhere else. Set decode mode, that's a function somewhere else, so decode, I guess. As you ate. Okay, this might be the key right here. You take some variable, you're passing in whatever this U8 is. Where's it getting that U8? Because declaring it as U8 makes me think it's like imported, like it's Python. Oh, interesting. You get an error. Different kind of data error depending on where the error exists, SPI or not. I'm not seeing that U8. I should probably search for U8. It returns nothing, I believe, just an error if it fails. Okay, yeah, that would make sense. Yeah, this right here, this nomenclature. max digits as U8. So max digits is the data size U8, which is also declared here. It's kind of like defining that function, not function, that's constant as a particular data type. Let me go to the top of this page. U size 8. So it's already U8. Maybe that's not quite how it works. My point is embedded HAL blocking SPI write. Embedded HAL digital v2. Apparently, Embassy uses the embedded HAL still to make these functions. So we should have the same data types. Allegedly. And here's the comma. U size is not, that's right. U size is what? The base size for your operating system, or your board, whatever system, your target, there we go. U size is the max size. Is that what it is? Hold on, what am I looking for? I'm looking for this. I think this is my issue. Mismatched types. Oh, you declare different. Isn't this you declare different data types? Is that how that goes? Probably go here and do the see the syntax. Also, the fact that there's testing built in the Rust, that's awesome. Having all these external frameworks in C is very annoying. You gotta have a different framework for your Doxygen or your documents. You gotta have a different framework for your testing, unit testing. You gotta have a different framework for your linter. It's just built into the Rust. That's awesome. I need a search. Array? Is that gonna be a thing? It is. Let's talk about tuples. Array type, here we go. So you can write array type using square brackets. Okay. So they have it here. There's 5 of this data type. This one is they have, okay, you can also initialize an array to contain the same value for each element by specifying the initial value followed by, oh, so this is 5 threes. That makes so much more sense. No wonder. 2 A5s. Yeah, that makes sense. Huh. Apparently it can take that. Interesting. Was that the magic sauce we needed? Was that the magic sauce? It compiles. It compiles, huh? Okay. And it's showing 2 5s. Wow. Okay, so there's a syntax thing that I'm doing wrong here. But you can see here, we got data, right? We got 2 A5s, and it's fine. So how can we make it different values? we can do that, then we're pretty much set. So if I do this, like I kind of wanted to originally. Okay, maybe it was this, and you know, I had one as mutable and the other one not. Cargo run. Go back to the waveform. There it is. A55A. Okay. A55A. Let's go and check something off of our list then. Because to me, that looks like a W. Where's our OneNote? I closed it. No, our OneNote's right here. Here we go. All right, so we said validate SPI outputs with boilerplate Rust. A big ol' checkaroony. Waveform logic analyzer, checkaroony. We gotta write FFF now on this. So, not really sure how we're gonna do it, but we need to. I mean, I kind of know how, but yeah, that's needed. So we got this test array. We can probably get rid of hello world now. Get down to business. So we get rid of loop as well. We no longer want that. So this was how we wrote to the SPI. Let's go ahead and create our new display element. This is where we're going to implement. So we're going to implement this library, this display library. Get the config, no, sorry, the cargo, and we're going to need to import this. Our boilerplate, I kind of keep together. Any new stuff, I like to put at the back, probably put it at the top actually. These are all boiler. Oh. Okay, yeah, those are all boilerplate. We're gonna put the new thing here. I think it's called mat. We're gonna have to look this up actually. What do we call it? On the crates page. No, that's the data sheet. Max 7.2. Max 721 0.4.2. Okay, this is the library we want. We're going to import that. Use max. Oh, it's not loading. There we go. Let's go ahead and import all that just for now. So we want to make a display. Mute my display. And this is gonna be max. This? No, that's a struct. I think we're gonna need to go to something new. No, yeah, we're gonna need to go to the library here. And better yet, let's go to the main page. You see a struct here. We have a power on. Implement the max 7.2. Maybe it is just this. Public struct. Is there a new? Is it from SPI? Okay, implement SPI max 7219 where SPI write U8. This is a exercise for me to see if I understand Rust enough. This one's from SPI CS. So this means you implemented the CS, which we did. So I think I can do max this from from SPI CS displays. Okay, how does it do this? Displays use size. Construct a new 7219 driver instance from SPI and CS. Number of displays in series. Oh, okay. We just have one. We have one display. Even though It shows 2 here. We're counting this as 1 because we actually only have 1 chip. Now, if we had multiple of these chips, then we would have larger amount. Okay, SPI, I called it my SPI. CS, we called it CS underscore display. Easy enough. Easy enough. We may need to do unwrap on this because of what it returns. I'm pretty sure. What am I looking for? I am looking for the different write functions. This is actually a big one. Set test mode on or off. Don't want that. We just kind of want to write something. Well, we need to power on actually. Power on all connected displays. Okay. So my display apparently works. So if I did my display dot power on, does this return? This returns a result, so we're going to unwrap that as well. Unwrap. We're going to do that over here. Oop, that does not work. Trait bound data error format is not specified. Is it because this has a data format that's not a basic one? Apparently SPI did. If I do dot unwrap on this, probably fine. Power on. I didn't like that data error. Let's read that again. Unwrap. And okay, so bound data error format is not specified. Oh, it needs to be one of these. It doesn't know data error. Data error is defined. It needs to have format. Okay. No worries. Unwrap. We unwrapped it. We created these. We now I think we don't even need CS display anymore. I think we just call this function my display dot write hex. The address will be 0 because we're writing to the first screen that we have, and then the integer a32. So we're gonna do FFFF. 1 2 3 4 1 2 3 4. Okay, what is it not like? Result them. Oh, we need to do unwrap again. Test array isn't used. That's fine. My SPI should be used. Oh, it doesn't think it needs to be mutable. Okay, sure. Fine by me. No squiggles. Seems good. Unused import, that's fine. Okay, it created it. It flashed it. If I were to run this, we do see data coming out. We do see data. Let me swap over to the waveform. Okay, so we see some data. Can we make sense of this data? Well, the first thing is, it's not actually showing me what's going on. Oh, this is an active low chip, I think. Okay, so instead of active high, active low. Okay, H2, H7. Anybody see that? We got, let's do shift. Is that how this works? Yeah. We record some data, and then we're just gonna pass through. What the heck? Why is it? Okay, there we go. I don't know what that reading was before. Okay, can I? Here we go. All right. So it might be a little bit tiny on your screen. I'm not sure. Fortunately, this tool is. Oh wait. Zoom is just that. Yeah. Okay. Never mind. Sorry. So our data looks like this. We have hex 9 followed by zeros. Hex 9 followed by zeros, then hex 8 followed by 47. Hex 7 followed by 47. Hex 6 followed by 47. Hex 5, 47. Hex 4, 47. 3, 2, 1. 9. 9 again. 8, 7, 6, 5, 4, 3, 2, 1. Okay, I'm going to make a hypothesis here. I'm going to make a hypothesis, and we're going to see if the datasheet matches. Based off of that behavior, this is what I think the chip does. Okay. Let's do a new page on this. New page, we're going to say Max. This is the name of our chip, Max 7219. Display driver. Seg 7 segment IC. Driver IC. I always have naming problems trying to figure out the right names I want for stuff. Okay. Let's try. Yeah. Okay. So we can see that there's 2 bytes. There's byte A and byte B in that SPI message we were seeing. This one was decrementing from 9 to 1. We have a total of 8 digits. Okay. This represents each digit position. It's indexed 1 through 9 for some reason. I would expect it to be 0 through 7. Hold on. 0 through 7. 1 through 8. That's true 8 digits. This is 9. Oh, the decimal point. Right? If we have a 7 segment display. Well, hold on. This is 7. And then the decimal points here. That's 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 values. This one was consistently hex 47. Okay. Hex 47 is the same as 0, 0. Is that right? Yeah, 0, 1, 0, 0, 0, 1, 1, 1. And if we're trying to make F, to me, that is 4 total segments have to be on. Oh my gosh, I keep hitting this scroll. Okay, this is 4 total segments. 4 total segs. Take it as you want it. So, in terms of the bits that are on, there is 4. And if we're counting based off of our convention here, this would be bit number 5, 6, and 7 have to be on. Bit 1 has to be on. I'm going to guess that this is decimal point right here. And that if we were to do like letters instead, this would be A, B, C, D, E, F, G. Okay, we're gonna erase this and put letters instead. I'm pretty sure this is right. This seems right to me. A, B, C, D, E, F, G, and this is decimal points, DP. It's a little messy, but you get the point. Fortunately, I have OCD. And I gotta make it neat. Okay. So, A, E, F, and G, they're all on in the value 47. So, if this is just cycling, like it should be, through all the digits, this should be working code. The only thing that I don't quite understand is in this waveform right here. In this waveform right here, it's showing the 9 happening twice. You see this? 9 is twice. And it's also 0 on those cases. Oh, you know what? Start and stop. Start and stop. So hex 9 maybe is the start of a data frame that you're sending to the, sending to the chip. So 9, it's the end frame. So you got 8, 7, 6, 5, 4, 3, 2, 1, and then 9 again. 9 again with the double zeros. Okay. This is the hypothesis. Let's just quickly look at the data sheet of this thing. And then we can just hook up the wiring. I think this is probably it though. It's looking pretty solid. Data in. So we need to go to the section of this data sheet where they're talking about the data. This is the pinout. Oh boy. I wonder if this is going to be a problem. 8-digit drive line, sync current from the display, common cathode. My display might be common anode. There is a very possible chance that the diodes are in reverse polarity. The only reason I don't know if that would be the case, or I don't think that's the case, is because we saw lights turn on earlier. So, yeah, that could be something. Yeah, what are we looking for? We're looking for, we got a shift register. We got a few different registers here. The format, it's 12 bits. It's 12 bits. There's an address, which that matches what we saw. 0 through 9, or 1 through 9, sorry. And then the actual data to accompany it, which would be 47 on some of these. What do we got here? Address. When it's 9, decode mode. There it is. 9, decode mode. Digit 1, 2, 3, 4, 5, 6, 7, 8. It's adding up perfectly. If you want to change the intensity, you can. If you want to change the scale limit, you can. Shut down, I'm not going to be doing that, but you can. If you want to do the test, it's just F. That's nice. We now need to see 47. We wanted to do F. Where is, do they have something to showcase F, or are you just gonna have to assume? Looks like you're just gonna have to assume. Let me go back up real quick. If it was E, oh, here we go, F. A, B, C, D. Oh, this is the on segments. So if you're doing E, it'd be the same, just have one more for D on. So let's look at E. You'd take D, turn it off, and then you'd have three ones, a 0, 0, 0, 1, and then another 0 for decimal point. Yep, this is exactly right. Okay, I'm pretty confident. We just need to now figure out the wiring, and then we're good. So I need to swap my logic analyzer with these pins. Where's the IC? Hold on. Here we go. This IC here. We need to unplug the logic analyzer and put it in on these exact pins. So what I'm going to do is actually put them... Oh! Like that. You see that? I'm shorting myself. Electricity is flying through me. I don't know what to think about that, but that's something. Anyways. Okay. So ground. Oh, we don't have a ground. No, ground wire is this one. Okay, yeah. So ground wire. In fact, it's probably better that we turn off the power instead of just sitting there with that on. Clock. So I think our problem was this is active low. When I was writing it the other day, I was using it as active high. Okay. So if we follow along, chip select is this pink wire, which is the same as the bottom left. So we're gonna take this pink wire. We're gonna kind of jam it in down here. So that way we can still monitor it, even though we're not connected to it directly. We're connected to it through the breadboard. Data out. This is going to be our data in, actually. Data in is going to be green. I'm going to take this. We're going to put it here. We're going to stick this here. I could just wire, that'd be good. All right, that's in. Take this purple. This is going to be data out, which would be associated with this. We don't actually have a wire for that. Okay, and then we got clock, which is the brown. That's going to go. Maybe not a lot of room for this one. I see a spot. Okay. Go right above it. And now we just need to ground it. This ground can just go into this ground, which then this can go into this. If I hooked it all up correctly, that should have turned it on, but it didn't. Okay. Oh, shit. Oh, shit. There it is. There it is. Can we get some F's in the chat? F, rip bozo. We get some F's going here. Damn. Okay. Okay. We got a nice F in the chat. Thank you, Zest. Thank you, thank you. Damn, bro. That, my friends, hold on, we get the full screen. That, my friends, is a nice set of Fs right there. I love to see it. I love to see it. That deserves a big old check. I check a Rooney. Yes. Thank you, Lag. That's so serious. We love the Fs. FFF on 7 segment. Validate with our eyes. As I'm freaking coming out of frame on this stream. That's a completed checklist for a stream. That's a good checklist if I do say so for myself. Damn. Look at that. That's probably the first time I've ever set a goal for myself and met it before the deadline. Very impressive. I'm going to pat myself on the back for that one. I take my sweet time, but the understanding popped out in the end. Well, shoot. What other functions do I have available? You know, what is at my fingertips now that I got this working? We're going to go ahead and get rid of some of these other functions we're no longer using. I mean, that's a hard-coded value. That's probably bad practice, but you know. What else we got? My display dot set intensity. Okay, let's try and make this brighter. How about that? What value can this intensity be? Well, tell me no. Comma. I was hoping it would say if I put 0.1 here, what's gonna happen? I'm curious. It's saying it needs a U8 or U8. So what if I do that? And we do unwrap on it too. Do I need to constantly call set display? I feel like I only need to call this once. If I were to guess, I'd only need to call this once. Oops, 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 oops. There's too many things getting deleted at once. Okay, we're gonna call this. Hold on. We're gonna yank this and put it right here. Good old Vim. Okay. Make it nice and neat. We're gonna rerun this. Oh, hold on, I didn't like something. What's this? Use let. Oh, we didn't do unwrap. Unwrap. Did it get brighter? Did the Fs get brighter? They might have. They might have got brighter just now. That's fine, we don't need that. Okay, so if that's 1, what happens if we write 2? Or how about better yet, how about we write N? Which is actually, in hex, that would be 15, 16, be 16. I can't tell. It looks less bright, if anything, right now. We'd have to look at the data sheet to see what the intensity actually results in. Are they warm? Nah, not really. Let's look up intensity. The control registers consist of... Okay, well that's just listing off what they have. Intensity register. Intensity register set to its minimum value. What's the maximum value? Oh, here we go. It displays brightness based off of the external resistor. Can be controlled digitally using the intensity register. The lower nibble. Okay, so the bottom 4 bits. Or bottom 4 bits. The modular scales the average segment current 16 steps from maximum down to 1/32. Okay. So you can't use this. So when I put it to 1-0, it's really just 0. So this is the dimmest it can get. If we want it to be the brightest, we have to write F. See, that's why you read the data sheet, everybody. Now watch this break because I'm overloading it. Oh my gosh, totally. I was watching it when it uploaded. That thing is way brighter. Way. Oh, wrong one. It is way brighter. We'll do full screen of it before and after. Before this is brightest. And this will be less bright. See that? Very subtle. Least bright. Actually, no, 0. 0 would be least bright. Sorry. It goes even, you know, dimmer than this. There you go. Least bright. Least bright. Now we'll do most bright, and then we'll just kind of keep it there for now. But least bright. Ooh. When you're programming, it gets all glitched out. Most bright. See? You can tell it's going through me. So much light that it almost looks like it's going through my fingers. Sick. See? This right here is why I love embedded. It's real. I'm touching it. It makes noise. You could try to do that with your software website, but you're just going to be punching your monitor. This is hardware, get it? It's hard. Anyways. Sick. All right. This definitely will be going on GitHub, I'm thinking. How would you organize this now? If you were really making something, how would you organize it? Because this is a very debuggy, this is a very amateurish way of, you know, working on this project. Let me put this at half. What's half of F? That would be 8, 7, 7. Our goal is to make a chess timer, meaning I have a button on each side. If you've ever seen the game of chess, there's 2 people, there's 1 timer in the middle, one side makes a move, and they press a button that stops the counter from going down. Then, when they press that button, it makes the other person's counter start to go down. And I want to do that where you can use this as a Rust chess timer. Okay, really simple board. It just takes this IC, a resistor, these 2 displays, and then just some buttons. They're buttons or a switch. When they make the ones that you like press down like this, hold on, let me look it up. You know, chess timer. The good old fashioned ones like this. I'm pretty sure it's just, this is a rocker switch, which is really just a slide switch with a 3D printed piece on it that pushes it around. Right? I think it's like this, which I might make because I do have a 3D printer. I'm thinking about putting this into a box and making it. But yeah, this is the side view of a slide switch, right? Your switch is on this side. You can have a 3D printed piece. I'll try to make a different color here. You could have a 3D printed piece that sits like this. Something like this. That when you press down on it, okay, somehow you would have to get it to move over here. The idea is when you press down on it, it creates a force that pushes this way and ends up over here. The bad drawing probably doesn't make a good explanation of this, but it's cheaper to utilize an existing mass-produced switch like this rocker switch, converting a slide switch, than somehow creating a brand new switch. Maybe it's more like this, where you have a much bigger surface that then gets pressed down, and it just so ever slides it, because the only possible movement is for this thing to go this way. Otherwise, this piece of plastic right here can't actually move. If this was stronger, this piece of plastic right here wouldn't move at all. But yeah. Anyways, feature implementation. Rocker switch, slide switch turned rocker. Okay. At least that's what I think is underneath the guts of this thing. I mean, it's huge. So it's like, how do you make that tiny little switch get moved by this giant surface? This one's using buttons. That would be a cheap implementation, but the rocker switches feel so good. There's also the chance that there is just buttons on each side, which, you know what, you'd probably save mechanical like lifespan, because this thing is getting slammed. You know, when it's close to the end of the game, you make your move and you hit it. You make your move and you hit it. You do it really fast, back forth, back forth, back forth. I kind of think that if it was a slide switch, that could be not so great. I'm like, now I'm going back on what I was thinking. As soon as I saw the one with buttons, I just kind of relapsed. Well, okay. When we get to the designing of that, we will think about that. We're not at that point. Just fine. But anyways, that's the chest timer. So if we got this code here, we can't just put everything in main. We gotta be a little more creative. We're gonna need to make some timers. How about this? Let's go back to the drawing board real quick. Let's make our chest timer. Chest timer game plan design, code design, or code. Yeah, let's just do code design. We're gonna need some things. All right, some capabilities, not in red. That's bad luck. But in white, titanium white. Okay. Capabilities, or rather software pieces of the software, right? Software components. We can talk about that. Components. That's okay. So we needed to figure out how to make SPI, which we did. Okay, so we can check that off. We needed to know how to make the max 7219 work, which we did, so check on that one too. We're gonna need to do some hardware timers, which I have done in the past, but they were not very precise. So we'll have to see, I guess, on that one. Hardware timers. We're gonna need to handle debouncing, so physical debouncing if we use buttons. Because those little things, they like to sit and bounce around there anything else? It's a pretty simple project, really. It's just a timer. It's just 2 alarms with some logic. Yeah, I don't really think there's much to it. If we were designing it from like a code level point of view, we have our main.rs, right? Main.rs. Do we want stuff in another file? If we're going to refactor this, I've never done refactoring of Rust code. If this was C, let me think about it if I was doing it in C. How about that? So we have main.c. .c. Arrow got erased there. Let's put that back. Main.c. Main.c, I'd probably put obviously our entry point. We would need to do initializing for like hardware settings. And then we would need to do like application app.c or like game logic.c. Well, that's okay. Hold on, there's no game logic. Clock, maybe not clock. Debounce. .c. There might be a library for this, so I might not even need this. This is a question mark. Hardware timers, that's handled by this. Yeah, main.c would have hardware timers already in the initialization. We have this loop here, of course. Custom driver, possibly. I'm trying to think if I'd want my game logic, because we just have our buttons. All right, you got your buttons times 2. You got your display times 2. That's it. This might all be able to fit in main.c. There might not be a need for refactoring. I was kind of thinking like, what if you did it where you had like a game layer or application layer? I'm not totally convinced on that. I think we start with main. I'm fine with it being in main. If I see a need to move it out, I will. But I think this is the game plan, at least. It looks fine having it like this. Yeah. But okay. I mean, yeah, this is really good. It's a good stream. If I get the hardware count down, then that's even better. But that'll be for next stream probably. I'm thinking that this is a good stopping point. If I open up another can of worms, it's going to take a little bit. Hardware timers takes a little bit. And I think, you know, I'm a little bit tired. I kind of want to say that for next stream. But it's a lot of fun. Let me put this on GitHub. How about that? We'll do that right now. And get rid of this file. In fact, we can actually get rid of this, use deformat. We're not even using that anymore. Let's do some comments. It's always good to have some comments in your code too. So initialize ACK and LED. Actually, we don't even need LED. Board LED. I just get rid of the LED. I think I just get rid of the LED actually. Yeah. Initialize. Create package link. Create peripheral access crate variable. Then we will do create SPI conf and freak. Let's see. operation frequency. And then we will create little initial SPI module, SPI and CS things. Create max 7219 instance based on SPI. And then we will do power on display and set to 50% brightness. Right. Yes. Cool. Infinite loop. And then write F to all digits on display. All right. That looks good to me. So then we need to somehow put this on Git. We're going to do a Git push origin main. And this is where things will get interesting. Source ref spec main does not match any. So we need to somehow link this to GitHub. Am I logged into GitHub? This will be sick. Put my first ever Git. Sorry, Rust project. This will be chess timer -rs. Public. No. Yeah, this is fine. I'll just create this for now. Existing repo from command line. Git remote add origin. Git remote. Now git branch -m main. And then git push -u origin main. It did not like that. Source ref spec main does not match any. Really? Now what the heck does that mean? Upstream, that's what this would be, yeah. Let's go ahead and search that up. Maybe you just need, oh yeah, I do need to commit lol. Commit git add. We want all, let's try to do it without, let's do the git ignore on cargo lock. I don't think we need to add that up there. I'll default it to be up there. If I look up a Rust project, is that going to be in it? I go to here. It's not there. Okay, that's what I thought. Cargo lock. We don't want you. Git add all. In the working, yeah, that's fine. Git commit message. Created initial display of all segments. Rust. Git push origin. Right, they did U origin main. Okay. So now if I go to my GitHub and refresh this, boom shakalaka. We are live. Sick. First Rust project on my repo. It's a big moment for me. It's not nice looking. It's not neat in terms of organization, but it's there. Look at my portfolio. That one commit, boom. Rest is there. Well, that's cool. Okay. I think that is a good stopping point for this stream. We got what we wanted done. Wow, interesting. I forgot I had this with the stream chat going. But anyways, thank you for stopping into the stream. I'm glad y'all could share this moment with me where I made the Fs on the circuit. That's cool. That's fun. I like it a lot. I'll be streaming again on Thursday at 8:30, and hopefully we can get this thing pretty much squared away in terms of the code for the alarm. But yeah, huge gains. Well said, Zest. I agree. Yeah, make sure you guys, look into Rust if you want to get into this next wave of embedded stuff. I think it has some potential. Well, anyways, let me go back to this. Okay, anyways, thanks for watching.